series, Department of Chemistry webinar series. Here, I'm very glad to welcome Dr. Subash CK, the speaker of our session 7. He is actually the alumni of our own chemistry department. He took his MSc Tech from chemistry department. And another personality here is Dr. V. Sajith, associate professor and head of material science and engineering department. He will chair the session. This session, 7th session will be chaired by Dr. V. Sajith. Let me speak a few words about Dr. V. Sajith, the chair of this session. He took his MTech from IIT Madras in 2005 and PhD from NIT Calicut 2010. He did his postdoc in Rice University, Texas, USA. He is a visiting scholar in Department of Material Science and Nano Engineering, Rice University. His research interests are phase change of materials, thermal management of electronics, corrosion and wear resistance coatings, heterogeneous catalyst for biodiesel system, control of air or water pollution, interferometry, automobile engineering and nano fluids. He published a book on internal combustion engines with Oxford University Press 2017. He is actively involved in the research field and he got many awards during his career. Some of the awards are Sir Dorabji Tata T.R. Anandaraman Faculty Fellowship, Young Researcher Award 2015, Venus International Foundation. He was the best young teacher. He got the best young teacher award NIT Calicut during 2007-8 academic year. He also got the Bhagyalakshmi Krishna Iyengar Award for the best project in the year 2005 from IIT Madras. And many patents are in process under his laboratory. He was in media reports for the development of nano coolant for the thermal power plants. And also recently for the fabrication of emergency ventilator with exhale disinfector. And he also had projects with different sponsored agencies like National Agricultural Science Fund, ICICA, DRDO, National Thermal Power Corporation, KSCSTE, and Tata. So he is also closely associated with the chemistry department. He has active collaboration in research with our department. Sir, I welcome to this session, and also I welcome you to chair the session, sir. Thank you.
Thank you, Dr. Sajith. And I would like to congratulate Dr. Sajith for arranging this type of webinar, and which is very much useful for the active researchers in our institute. So I hope that you will be able to continue this task in the future also. And research now how to chemical science or nanotechnology, very much essential to have a good understanding on the various microscopic techniques to characterize the material, to know about the properties of the material or the composition or the morphology of the material, and not only the basic understanding about the microscopic technique. It's very essential to have a good. So in this scenario, this webinar on microscopic techniques for material characterization is very much relevant, especially from a researcher who has more than 9 years of experience, hands-on experience in the field of various microscopic characterization devices. So we have with us Dr. Subash CK. He is Adhoc faculty in the School of Material Science and Engineering, and I have great pleasure to introduce Dr. Subash. Dr. Subash is currently working as an Adhoc faculty at School of Material Science and Engineering, and he is taking care of the activities of Microscopic Center of the Institute. And he received his bachelor's degree in chemistry in 2008 from Calicut University. Then Master of Science degree in Polymer Science and Technology in 2011 from Department of Chemistry, NIT Calicut. Dr. Subash has completed his doctoral degree in 2017 from School of Nanoscience and Technology, NIT Calicut, on piezoelectric polymer composite for pressure sensor and energy harvesting application. He has published his research finding in 19 international journals and presented in different conferences. His publication list includes reputed journals in the area of materials chemistry like nanoenergy, ACS applied materials and interfaces, ACS applied nanomaterials, sensors and actuators, etc. His research interests include piezoelectric materials, ferroelectric, piezoelectric and contact electrification based basis for sensors and energy harvesting, polymer nanocomposites, nanomaterial synthesis and microscopic analysis for material science. In the beginning, he is having more than 9 years of hands-on experience in handling and demonstrating the sophisticated instruments like SEM, AFM, DC magnetron spectring unit, STIR, spectrometer, etc. So he'll be talking mainly about the scanning electron microscope and atomic force microscope in detail. So this session is for 50 minutes, and after that you'll have the question and answer session, and you can post your questions in the chat box also. So we'll be taking up that also. I recommend to talk on this topic, microscopic technique for material characterization. Dr. Subash.
Yes, sir. Yes, sir. Good afternoon, all. Thank you so much for the nice introduction from Sajith, sir. And I'm very happy and extremely happy and privileged to be a part of this seminar session of Department of Chemistry. I was an alumni of Department of Chemistry. We were the first batch of SMSE Polymer Science and Technology. So I would like to talk about the microscopic techniques which will be useful for material characterization. Okay, I will just share my slides first.
Dr. Subash, could you please switch on your video for a moment? Just switch on your video.
Sir. Yes, sir. So on, sir. Is it okay, sir?
Yeah. Okay. Continue.
Can I share?
Yes.
Yes, please share. Please.
Is it visible, sir? Hello, Subash, sir?
Yes.
Visible.
Okay. Thank you. So we will start with so I would like to talk about microscopic techniques for material characterization. And thank you so much for giving this opportunity to talk about microscopic techniques. Thank you, the HOD of chemistry, Dr. Sajith, and other faculties of chemistry department. Okay, we will move on to our regular talk. Okay, so I would like to tell one more thing. I'm dealing with some basic aspects of microscopic techniques. Here, a lot of experienced researchers and faculty members are present in this webinar. So please excuse me. I'm talking with the very basic things of microscopy. Maybe a little bit boring. So I will continue my presentation. So in between the pages, we can see the introduction of microscopy. and little bit history of microscopic techniques, because so how we evolved from a basic lens to microscopy, that is very interesting to study. Even though history is boring, still of how we have evolved from a bit of lens from a complex microscopic structure, that is very much interesting for me. That's why I would like to talk sometime for history of microscopic techniques. Then we will directly move on to scanning electron microscopy and the sample preparation and analysis. So we'll be giving a lot of demonstration here in our microscopic center for a lot of students from schools, from colleges, and our own research scholars. So I would like to share some thoughts of sample preparation and analysis, how we will analyze the material. So how we'll interpret some ideas of interpretation also, and then at last we'll go through atomic force scanning for microscopy, especially atomic force microscope. So as an introduction, we can classify characterization techniques into microscopy for imaging and spectroscopy for analysis. So we will be today we will be focusing on microscopy and a little bit spectroscopy also in the aspect of EDS and species spectroscopy, which can be used along with the FESCM analysis. And what do you mean by microscopy? It's very interesting to see the meaning of microscope in Greek. In Greek, micros means small, and scope means to look or to see. This is an instrument, viewing object that are very small objects, and which is unable to see through our naked eye or unaided eye. Okay, so this is science of investigating small object using such an instrument is called microscopy. And all of you know the term microscopic means minute or very small, not visible with eye unless by a microscope. We will be seeing very small objects through a different technique, microscopic techniques. So a lot of microscopes are available. So we will go through each one by one. Okay. So as I mentioned in the first slide, so it is very interesting to see how we evolved from a single piece of reading stone. In 1000 AD, the first visionary aid was invented in 1000 AD. So it is around 1200 years ago. So the first visionary aid was a reading stone. So actually it is not till now it is not clear who invented that particular reading stone, and later it was so we will be calling this as magnifying glass or lens and all. So why it is known as lens? It's because that particular reading stone has a particular shape of lentil seed. That's why we are calling it as that reading stone as lens. Then, so a little bit history about microscope. The trace in the energetic young scientist Furness, he mentioned in the book of optics in 2011 and 2021 the foundation of optical research on magnifying glasses, and also a device called reading stone by an unknown inventor. This reading stone still we don't know who was invented this reading stone. Thought to be that Ivan Furness, he explained in his book of optics, items book of optics, about this magnifying reading stone and all. And the compound microscope. Then initially they found out this reading stone as a piece of lens, so what we are calling as lens. And 1595, Hannes and Jensen, they found out a compound microscope which will be an array of lenses. They put an array of lenses and they make it as a microscope. You can see the microscope here. It's very interesting to see the evolvement of the initial array of lenses to our new model electron microscope and atomic force microscope. It's very interesting. And in 1631 in Holland, the Hannes and Jensen found out this first compound microscope. And in later in 17th century, Robert Hooke is a biologist, and he in England he found out another second type of compound microscope. And the important finding in the 1632 microbiology, Leeuwenhoek found out in another set of microscope that is you can see here. It's also very interesting. He tried to move the lenses with that screw and try to focus the material. So it's very interesting to see the evolvement of that lens to our compound microscope. So you can see the Jansen's first microscope here, the first compound microscope in 1595, and now we have a compound microscope like this, the optical microscope like this. And then the turning point came the optical microscope to electron microscope. So in 1920s, it was discovered that up to that time, the old microscopes are working under direct light only. Then they discovered that under very high vacuum, electrons are behaving like light. And they travel in straight line and have a wavelength which is smaller than that of light. And another observation they found that so up to that level we'll be using the optical lenses. Then another important discovery that was found that the electric and magnetic field have the same effect on electrons as glass lenses and mirrors have on visible light. Then these two turning points came into an important discovery of electron microscopes. So initially, we know that now we are regularly using the material science are regularly using FESEM, TEM, as well as AFM, etc. So this is the evolvement from a lens to these electron microscopes. It's not a easy journey. So you can see each scientists are doing step-by-step improvement, and they made in 1930s Rust electron microscope. It is actually a primitive model of a transmission electron microscope invented by Ernest Rust, and uses electrons rather than light. That is a major breakthrough and allows for the viewing of objects as small as the diameter of an atom. And he won Nobel Prize in 1953, and so we'll be using this transmission electron microscope for viewing very small objects. Then in 1981, the Binning and Aurora, they also got Nobel Prize in 1986 for inventing the scanning tunneling microscope. It's a type of scanning probe microscope. In our microscopic center, we have equipped with the scanning tunneling microscope, but it is along with our atomic force microscope itself. Actually, so we'll be calling together as scanning probe microscope. And this scanning probe microscope can be, the interest of scanning probe microscope is that we can able to view in a 3D view, and total magnification is very high, and atomic level we can see. So actually, the birth of nanoscience is due to this invention of electron microscope and scanning probe microscope. In 1981, they have invented the scanning tunneling microscope, and they won. within 5 years they won Nobel Prize in 19. So it's a that discovery is highly and a evolvement of new technology, that is nanoscience and technology. And you can see the evolvement, as I told, from a lens to optical microscope. It took long a gap. Then in optical microscope to different type of microscope. In TEM in 1931, that first primitive TEM came in 1931. Then SEM in 1942 and STM in 1981 and 1986. They found out AFM. This is a bit of microscopic history. So you can understand the difficulty they have faced in long before. 1080 itself started with a stone, and they found out a compound microscope. Then they make it as an optical microscope. Then the new inventions came on electrons. Then we can able to see in atomic level using different microscopes. So, just for an initial comparison, what is the major difference between all these kind of microscopes? Initially, we told optical microscope. It's obviously, optical lenses will be there, and through optical lenses we will be seeing magnifying, just magnification only, just like a magnifying glass. And compound microscope will be putting different lenses and focal length will be adjusting and seeing. And when we came to TEM, the main difference is in the place of optics. They changed into magnetic lenses, as well as the input. The input is changed from optical to electron. And SEM also, so we'll discuss the difference between SEM and TEM in later slides. Then they move to SPM, scanning probe microscope. Different type of scanning probe microscope we can able to see. One is atomic force microscope, and another one is scanning tunnel microscope. So in our microscopic center, we have equipped with the XC100 atomic force microscope of quark systems. In that, we can able to, if TIP is available, we can able to do STM and AFM in a similar systems. Okay, and so before going to scanning electron microscope, it's a very basic idea. So what do you mean by resolution? So everybody is talking about this for this microscope the resolution is high, for the other microscope resolution is less, like that. So we'll be always talking about resolution and magnification. So what is exactly the term resolution means? So it's very interesting to see the meaning of resolution. The term resolution, or minimum resolvable distance between the distinguishable object, that is known as resolution. So when we look into our common things, with our unaided eye, we can able to see 0.1 millimeter. And resolution for when we talking in terms of equation, a base equation is approximately it is lambda by 2. How much wavelength we are giving and what resolution we are getting, that is the exact point in this. So resolution D is equal to 0.612 lambda by n sin alpha. N sin alpha is known as numerical aperture, and so this is approximately around lambda by 2. And so what is the importance of this resolution? So as we told, we are why we are going to optical microscope to electron microscope. So that is very important. Whenever students are coming from schools and all, so first I will ask when we are giving a demonstration on SEM, why you are here. So it's very now almost all schools and all having optical microscope, and they are seeing objects in optical microscope. So now the school students they know what is optical microscope and all. So just I will ask initially. I will ask what is the difference between optical microscope and why you are here to see the electron microscope. So then initially we will be talking about this resolution. So we know by using optical microscope the maximum magnification is around up to what resolution we can able to see. That is very important. Around 200 nanometer to 50 nanometer we can. When you are going to electron microscope, it is very less. So even now, I think for new models are available. 0.5 nanometer below, better than that, we can see with the SE. So that is the importance of resolution. Then, so we'll move on to what is the importance of microscopy and resolution. So first point is what do you mean by magnification? So we know that image size by object size is known as magnification, and the resolution is the fineness of detail that can be distinguished in an image. So highest typical resolution, as I discussed in optical microscope, it is 200 nanometer, and electron microscope, it's so we can able to approach up to 0.1 nanometer. So it's very interesting to see the difference between optical microscope and electron microscope. And so slowly we will move on to SEM. So you can see this image, our own SEM system in an Calicut. We have a center at Calicut. So our own SEM, I have put an image of SEM. And you can see the roadmap of SEM. In 1935, the scientist Knoll has initially established some possibility of integration. And then they have worked on in 1942, 50 nanometer resolution developed. And in 1960, SE detection. So I'll let you know what is SE and you may know what is SE and all. Then 1963, 5 nanometer resolution SEM developed. And in 1965, a commercial SEM was developed in UK, Cambridge, UK in 1965, and 1968 SE detection from inland samples, and in 1971 FESM. So we have an FESM here. In 1972, commercial FESM they manufactured, and 1986 resolution is gone up to 0.7 nanometer. That is the interesting factor. So you can see the 1935 to 1992. So it's very recent. 1992 is we can talk it as very recent. And so our model, this Hitachi SU6600, what you have seen in this image is 10. So you can see the gap, generation gap, 1935 to 1992. And so we should talk about the very basic principle of SEM. As I'm talking about scanning electron microscope, I can't able to go without sharing the principle of scanning electron microscope. So obviously, an incident electron beam will be falling on our bulk sample. Bulk sample in the sense our sample what we are placing. So different type of samples can be analyzed by using SEM scanning electron microscope. So I'll tell you one by one. And the incident electron will be falling on bulk sample, and we'll be getting lot of different secondary electrons and secondary atoms will be coming out from the bulk sample as secondary electron and as backscatter electron and characteristic X-ray and cathodoluminescence and continuous X-ray, Auger electrons, etc. Lot of outputs will be getting from the sample. Okay. So each of these outputs can be captured and can be analyzed. That is very important point. Each of these outputs can be we can able to capture and we can analyze it properly. So basically, for imaging purpose, we'll be using this secondary electron imaging as well as at some point we'll be using backscatter electron imaging. And for as I told in the initial slide, so for if you want to know what all elements present in your sample, what all elements present in your sample in quantitatively as well as qualitatively, you can go for X-ray analysis. That is known as energy dispersive spectroscopy. So using that method, you can able to identify so what all elements present. So basically talking not that much quantitative, but at least we can call it as qualitative technique, but still some idea of quantity also we get it from the EDS analysis. Okay, so we will be scanning with an electron beam, and we'll be getting these outputs, and we'll be observing each one by one. That's what the basic principle behind the scanning electron microscope. So this is the configuration of scanning electron microscope. It's technology point is coming, and the high voltage we will be applying for as a filament. Filament will be there, and there is a cathode anode system over there, and this cathode anode system will be generating the electrons, and we will be giving an. So different type of SEMs are there. I will tell you what we'll be discussing, and the different aspects of each point I will be discussing. The first is electron gun, and then we will be going to the condenser lens and objective lens. In between, scanning points will be there, and inside the sample chamber we will be placing the sample, and the electrons will be coming as a straight line and falling on sample, and we will be detecting the different type of using different type of detectors, and it is amplified and converted into images. And about electron gun, it's very important part. Actually, we can classify SEM in terms of this source of electron gun. So you can see in that this table, you can see different kind of guns, tungsten filaments. From where we'll be making electrons, they'll be producing electrons, and that electrons will be. So initially we have tungsten filament, so and LAB6 and cold Fe and Schottky Fe. So in our system, Hitachi SU6600 will be using this Schottky field emission gun, and another important point is the lifetime of each gun. That is also very important. So I hope you know the cost of scanning electron microscope. So in our system in 2009 when we bought, it is around 1.9 crores. So and in each 6,000 hours, we should change the electron gun also. Electron gun also costs 14 lakhs, 13 lakhs each time. They'll ask them change after 6,000 hours. The image clarity will be ruined. So we should change the electron gun each time. So that is very important. So and the difference between the tungsten filament and Schottky Fe filament is very important. You can see the different type of analysis. The tungsten filament, the tungsten filament SEM is known as thermionic emission. We will be getting a thermionic emission from the tungsten filament, and Schottky Fe field emission. So when field emission comes, an extraction voltage will be giving for attaining the electrons from anode part. Okay, so due to this extraction voltage, we'll be getting more extraction voltage, we'll be getting more electrons, and we'll be getting more clarity for field emission through the field emission gas. So, and another important factor, you can see that tungsten filament is an hairpin like structure, and the tip of that hairpin you will get you can see the Fe filament also, and using this Fe filament we will be producing electrons, and we are giving an extraction voltage, extraction voltage. That's why these electrons will be streamlined to our particular lenses, and the anode apertures will be there in between to streamlining the electron beam, as well as lenses will be there for focusing the beam, and it will fall on the sample. And after falling, the primary fall of electrons, some secondary outputs will be coming, that will be detected by our detectors. Yeah, you can see this image. It's broken. The TP is broken by excessive use. It's an SEM image itself. By excessive use, the TP will be breaking, and we can't able to use further. This. So before breaking, so we can able to see the clarity and the sorry, not the resolution wise, we can able to understand the quality of the image quality will be reduced after some 6,000 hours. But still, the company will be telling us as 6,000 hours. Still, we are using 4 and 5 years with the same electron gun. Still, we are getting good images. But if we change the properly, you will get better images, you will get better resolution, and it will be useful for our further research. And the resolution with various type of SEM. You can see the thermal SEM. Thermal SEM means thermionic emission SEM, the tungsten filament. You can see the resolution point, the acceleration voltage at the bottom. The resolution point is very low for thermal SEM, and in-lens FESEM is giving better resolution. And even the different type of lens systems, if we use different type of lens systems, we'll get better resolutions. And we discussed about how the electron is formed and it is coming and falling over our sample. Then we will be moving on to how the image formation is taking place. So we, as we discussed the matter-electron interaction. So when the electron beam is falling over the sample, we will be getting inelastic collision with the backscatter electron with elastic collision, and secondary electron with inelastic secondary electron with inelastic collisions. So these usually, so what we are using is we have different kind of detectors in our system. So usually for imaging, we'll be using backscatter electrons. So you can see the image of detectors for our system itself, Hitachi SU6600. You can see the detector part. Different detectors are attached. We have 3 different kind of detectors. We have a secondary electron detector for regular imaging. We'll be using secondary electron detector for regular imaging. And for some particular kind of for some samples, so the sense we want to know the compositional difference in image itself, we will be going for BSE imaging, backscatter electron imaging. And for X-ray analysis, we want to know the elements present in your sample. We go for EDS analysis. That bigger one, the blue one, is EDS detector. So we'll be installing a new EDS detector to our system. So very soon. And so you can see. So what do you mean by what is elastic interaction and inelastic interaction? Due to elastic interaction, we will be getting BSE. So when atomic number increases, so BSE signals will be more, and increase less, BSE signals less. So we will calculate. Sorry, we will imagine accordingly. So the contrast or compositional contrast we can easily understand by BSE imaging. For other regular surface imaging, surface morphological imaging, we will be using secondary electron. And so while doing SEM, so we will start from the sample preparation. That is very important. So it's very basic thing. And another important factor is for SEM, scanning electron microscope, the sample preparation is very easy. So there is no difficulty in sample preparation. Very easy. There is no complicated techniques. But we should have some care on the sample preparation also. Otherwise, we won't get images. So basically, we are using carbon tape, say ghostly tape, double-sided conductive tape, and we will be placing it to our. This is known as stub. So for each instrument, the stub size and stub style is different. But for what we are using is I have put a photo of that. And we'll be using these kind of stubs, different diameter stubs, and we can put n number of samples, different number of samples by putting tape, carbon tape like this. Okay, so we'll be numbering one by one, and we'll be observing each number, and each number you can able to see it in the microscope, and we'll be observing each one by one. That is the usual method. And another important factor is known as sputtering unit. We have gold sputtering as well as carbon sputtering in our facility. And the gold sputtering, usually we'll be going with the gold sputtering. So why we want to work with gold? That's an important question. So if you are working with non-conductive samples, so you should go for gold coating. If you are working with conductive sample, it's very simple. So we are just putting our sample over this conductive tape on stub, and we'll be directly analyzing the sample. But if you are going with non-conductive samples like polymers and some other biological samples, we'll paste the material what we want to observe on the carbon tape, and we'll go for gold sputtering. And this is known as stub holder, and we'll be placing the stub over stub holder, and we'll go for analysis. That is the usual procedure what we are doing here. This is the procedure what we are doing here at our microscopy center. In each model, the stub style and stub size is different, so they'll be having their own idea, their own procedures for sample preparation. So, but in our facility, we have only this this hand sputtering unit. So, for drying and all, so you should dry the sample and come with dried sample, and we'll be doing the analysis. So there are 2 points. So before going for analysis, we should understand 2 points. One, the sample should be completely dry, because the instrument is working with high vacuum. During our discussion about principle, I told the instrument is working under high vacuum. So, so obviously, so we will be using completely dried sample for analysis. Without drying, we can't able to use. There are some other methods are the variable pressure mode scanning electron microscope and environmental SEM. There we can able to look a little bit water content samples also. So for nanoparticle encode, what we are doing during sample preparation, so we'll be dropping the sample over this carbon tape. Otherwise, you can drop the sample after dispersing your nanoparticle in a particular solvent. Most likely, we'll be expecting it to easily evaporating sample, easily evaporating liquids like acetone or alcohol or something like that. Otherwise, even water is also fine for us, because we will drop it in water and we will be dispersing the sample in water, and it will be dropped over the carbon tape, and we will be put it for overnight drying. And so if you want to do the nanoparticle samples, you should come with the well dispersed sample before day. If you want to do it tomorrow, you should come today itself, and we will be preparing the sample, and we'll be putting it in desiccator, and we'll be analyzing the sample in the next day. Okay, so we prepared the sample, and next is imaging. This is a photograph of our own system, and the first of all, you should think about mode of operation. So which mode you prefer to operate? Either secondary electron imaging or backscatter electron imaging, or EDS, X-ray analysis. What you exactly required for your sample. Then the next point is accelerating voltage. That is very important. It all depends upon your sample. So which type of sample you are bringing, and so we'll be changing the acceleration voltage with the with our experience and the sample properties. If you are coming with polymer samples, you will be giving very small acceleration voltage. Actually, we can change acceleration voltage from 0.5 kilovolt to 30 kilovolt. So for polymer samples and all, we will not going beyond 5 kV up to 10 kV. For some samples, we go up to 10 kV. Usually, 1-2 kV is enough for polymer or biological samples. And next point is working distance. Working distance means the distance between the bottom lens and with the sample surface. So that is also very important. So If you are going for very small particles in the sense nanoparticles, will be going very near to our sample. So approximately 10 millimeter distance from the lens and the sample. Even 5 millimeter is also fine. For other samples, for metallic or big samples, it's not good to go in that level. So if you want to see the whole surface, you will place it in the more distant. Okay, and then next is magnification. So some students will come with specific magnifications. Otherwise we will select some magnifications and we will do the analysis. You can sit with us and you can see the analysis and you can give us suggestions and you can even so you can't able to operate. So we'll be operating and you can some suggestions. So if you need some particular kind of image, we're ready to take those images. And next point is image capture. We'll be capturing the image and we'll be giving. Okay. And the important aspect of acceleration voltage, as we discussed, you can see, you can understand very easily from this image also. This is in very low acceleration voltage, and this is not that much clear. And some issues are also there in the image also. And you can see better image in the second image. So we will be increasing the acceleration voltage. Here, from here itself, you can understand the acceleration voltage. We will be actually changing the acceleration voltage with our experience. Each sample will be applying different kind of acceleration voltage. And you can see from this image, influence of acceleration voltage and specimen atomic number. This is easily understandable. Lower acceleration voltage and this one is higher acceleration voltage. And low atomic number, it can penetrate very easily. So for higher atomic number, the penetration will be less. That's what. And next point is, as I told, working distance is very important. So when you are changing the working distance, the depth of field. So depth of field means how much area you will be, the clarity, the focus, how much area will be focusing under the lens. Okay. So depth of field is also very important. When you are increasing the depth of field, working distance also change. So first image is 3 mm working distance and the second one is 12 mm working distance. So it's all about what you require. Actually, so if you need a close view or you need a it depends upon the sample and the requirement. And the next point is what we have mentioned here is stigmation. Stigmation is also very important. Irregularity in lenses, we can correct it, and the corrected one is you can see the difference in each image and easily understand what is the how we are doing the stigmation. So while doing after inserting the sample, we'll be deciding acceleration voltage, working distance, and stigmation. We'll be adjusting the stigmation. Then only you will get the perfect picture. Then here also, so it's very important to adjust the contrast and brightness. Automatic bright contrast control is there in the system. Still, we will adjust the contrast and brightness by our own hand. And this focusing. So when you are doing an analysis, hands-on, we are doing the analysis. By doing multiple samples, we will get an idea of how we will focusing and all. So this you can see under focus image and over focus image and just focus image. We should capture from the focused image and we should adjust the contrast and brightness. That is also very important. And I will like to show some images what we have captured. I have put only our own images what we have done it in our SU6600 SEM NID Calicut SMSE. Okay, so these are some biological samples. These images are in 2010 or 2009 only. So it's old pictures. When you are getting the capability of our instrument, what I want to show this biological sample, you can see, you can understand what is this. This is an ant. And you can see these values are very important. Without this value, there is no meaning in an image. Without the, at least we should have this this scale. Okay, then only a image will be a microscopic image will be valid. So that is very important. That's why I put in my first slide itself, I put that scale bar. Without that scale bar, there is no meaning to observe a scanning electron microscope image. Okay, so the first one is this one is acceleration voltage 1 keV. So this because this is a biological sample, we are only applying a lesser acceleration voltage. We are applying only 1 keV, and this is known as working distance 9.4 mm. We can change up to 40 mm to 5 mm, 3 mm to 3 mm we can go, and this is known as magnification 70x only. This is very even can see with our eye, so that's why it's 70x only. SC means secondary electron imaging. If you are doing BSc, this one will be replaced. And for our software, from here to here, it is 500 micrometer. So each division will be divided by 10. This is 10 division. So each division will be 50 micrometer. So like that, you should analyze the sample. So this is very simple, very big sample, but when you are dealing with nanoparticle, and I will show you how I will be doing. And this is Jacob Food, and it's very interesting structure. We calling it as nano brush, and all. Using this brush only, it can climb over the wall. Here also you can see 200x, so better magnification. And we haven't changed the acceleration voltage because it is a biological sample, and the scale is changed. When you are changing the magnification, definitely the scale will change. And this is also interesting. This butterfly wing. So we are doing some experiment with the butterfly wing and all. So that's why we have done this. With our human eye, I will be seeing butterfly eye, and with microscope, I will be seeing the butterfly. Sorry, not butterfly eye, butterfly wing. Okay, sorry. We have applied 2 kV here, and we have applied 5 kV here. When you are magnified, we can able to apply 5 kV here. So for these samples, we will be sputtering. We will be doing sputtering because these samples are non-conductive samples. And we applied around 600. Magnification we fixed on 600 SC imaging only, and we can see the scale. And further magnification 5K, 5000 times magnified. This is 130x. This is 600x, and this is 5000x. So this is 5K. As you can see the difference. And again, we have magnified. This is a 10K image. So you will get the beautiful aligned structure of our butterfly wing. And up to now, we have discussed about the biological sample. Then we'll be focusing on metallic samples. We can see some metallic samples, the welding joints you can observe, and thickness of some coating also you can observe. So if the thickness is proper, you will get exact thickness. From my experience, what I would like to suggest is, so you should have a perfect coating, then only you will get the exact thickness. If it is irregular, it will be you should take different images of different doing cross-sectional imaging. Without if it is in an irregular manner, it's very difficult to find out the exact thickness of the coating. And cracks you can observe in metallic samples. And this is that's the finest application of our scanning electron microscope. So you can see the beautiful images like this is, you can see 150K times magnified image. We have done it in our own. These are our own samples from the School of Material Science and Engineering. We have prepared some nanoparticles, and we have observed this 150K times. You can see the scale 300 nanometers. So each division will be 30 nanometer. So particle, and this also in 50K. 60 or 50K, and you can see the scale 500 nanometer. Beautiful dendrite structure at 20K, 100K. And when you are magnifying it, it will be like this. You can easily observe the size, shape, and morphology, exact morphology of the particles. and it's a very beautiful image, 25K only, 2 micrometer scale, and this is another image at the same sample at 100K, and you have to observe the this one also, the acceleration voltage as well as the working distance. So we will be changing all these kind of things, and we'll be doing multiple samples. That's why we know how we want to change the working distance, acceleration voltage, magnification, etc. And we'll be doing accordingly, and we'll be getting focused images. And another point is polymer materials. So these are all my samples only. These are some porous polymer samples, and these are some polymer nanocomposite. You can see some particles over here, and these all are in different magnifications. And these are some polymer particles, PVDF particle, and bigger in lower magnification, not very higher magnification, lower magnification only. And this is polymer fibers. What we have done it from chemistry department itself. It's electron spun fibers with the help of Dr. Sajith sir. And so this is my own sample, PVDF TRF sample, and electrospun membrane. So you can easily apply 5 kV for this, and you can mark like this. You can analyze and mark the thickness of the fiber, and even you can mark the nanoparticle thickness. And according to this scale, we'll be marking the software will be marking the dimensions. Okay, you can see the scale. And when you are looking to natural, it's very interesting structures are available. We know about lotus leaf and all. Sujit sir is always interested in these kind of things. He is always coming to our microscopy center, and is taking these kind of images. And it's very interesting to see the structures, the protrusions over the leaf, and you can see this one is very important. This one is a tilted image. You can even, as I told, you can tilt the sample specimen and see the around the 45 degree, 50 degree. You can tilt, and you can see the growth over the surface. This is an interesting image, and seeing one particular bump will be focused, and we'll be taking these images. This is also very important. This is not from our these all are taken by our system, a different paper. And another interesting application is EDS and mapping, energy dispersive spectroscopy and mapping. So if you want to find out what all things in your material, we will go for elemental analysis. And if you are working with a polymer nanocomposite or any composite material, so if you want to see what each element where it is exactly placed in the sample, you can go for mapping. In here, it's an fiber sample. So when you are doing EDS, the acceleration voltage should be higher. Otherwise, you won't get the correct elemental composition. That's why image clarity will be little bit less. That's why the image clarity is less. But you can see each element where is exact, and mixed graph also. You can see each element. The zinc is there, fluorine is there, oxygen is there, carbon is there. Where is it exactly placed over the sample? This is very useful, and all nowadays all journals they are asking for the distribution of nanoparticle in composite material. So this method is very useful, and people are widely using this method for polymer nanocomposites. And these are the advantages of scanning an electron microscope, and versatile and with various modes of imaging, and high level of automation, and user friendly. It's user friendly only, and if you have some experience with some samples, you will be it will be easy for doing the whole type of samples. But different kind of samples you should have experience. Then only you will get that idea, and you can further you can do the analysis. And it's very relatively straightforward interpretation. Interpretation is very easy. So when you are working with some particles and all, interpretation is very easy. Even you will get the particle size and shape from directly. You are seeing the image. So 2D imaging only, and obviously the magnification and image resolution, and EDS for detecting the element in the surface. And I think it's already 4 o'clock, and still I will go for I'll go fast. Next is scanning probe technique. The next one is up to now we have discussed with electron-based microscopic techniques. From here onwards, we will be discussing about probe-based techniques. Scanning probe, it's a branch of microscopy that forms surface using physical probe that scans the specimen. Now onwards, we will be using a probe for analyzing the surface. And whenever we are discussing about atomic force microscope, its resolution is very important. 2 angstrom lateral level and 0.1 angstrom vertical level. And the important aspect is we can able to see the 3D aspects of your sample. In SEM, we will be seeing 2D aspects of your sample, and AFM will be getting 3D aspect, as well as you will get some values on roughness, as well as you will get some surface potential values. Those kind of things you will be getting from AFM. In scanning probe microscopy. But in the case of SEM, you will be getting the image as well as the size, shape, morphology, etc. How it looks like. Usually, you will be call it as morphology. Here in AFM, in the case of AFM, will be how it feels, the surface, how it feels, and the roughness of the surface, hardness of the surface. Those kind of things you can easily observe from the SPM techniques. We have an atomic force microscope here in our microscopic center, XC100 park system. This one also installed in 2009, 11 years ago, and we are extensively using in our research, and we'll be doing some external samples also, both SEM and AFM. And atomic force microscope in 1986 only, we have already discuss. Whenever we are talking about atomic force microscopy, will be comparing it with the blind man touch. Okay. So how the blind man reading the surface? So you know about brain language and all. So like that, a probe with a blind man touching with his finger, and this probe is feeling the surface, and he will be seeing the surface. The probe will be giving some output, and the probe will be touching the surface, and he will be giving some images to observe and analyze and research. And this is the real atomic force microscope. A microscopic cantilever will be there. On the tip of that cantilever, I will show you the image, and you can easily understand. This is the cantilever, and this will be the tip, and photo detector will be there, a laser beam will be there, and this cantilever will be focused. The laser beam will be focused on this cantilever, and underneath that tip will be there. When you are doing the analysis, the tip size is very small. You can see the tip size very small nanometer range. You can't be able to see the tip. You will be observing when you are doing the AFM analysis. You will be observing the cantilever, and you will be adjusting the tip sample distance, and you will be doing the analysis. That is the usual procedure. So here cantilever will be there, and tip will be there. You will be controlling the cantilever. Either you can move the sample, or you can move the tip. That is a very important thing. In our case, we are moving the sample. We are moving the sample. So samples, a different type of sample stage will be available under micrometer to 100 micrometer. If you want to move your sample 100 micrometer to 100 micrometer, you can move it. If you want to move the 5 micrometer to 5 micrometer, you can move with the different scanners. And we will be having a tip cantilever, and this tip will be on this cantilever. We will be seeing the cantilever, and laser beam we will be seeing. And by moving this one, with the interaction between surface and the tip, we will be getting some signals on photo detector, and it will be making an image. Okay, so how we will be feeding the sample. And this is the detector measures the cantilever deflection as the tip is scanned over the sample. Several forces typically contribute to the deflection of AFM cantilever. The basic force is obviously the van der Waals force of attraction. I'm not going to further more on this. These are the AFM tips. Usually silicon-based, silicon-based tips are using for analysis. For each analysis, we will be using different kind of tip. Different modes are there: contact mode, non-contact mode, and tapping mode. Obviously, the contact mode is having high resolution, but it will damage your sample. And non-contact mode will be bit low, but no damage to sample, and tapping mode better resolution and minimum damage. We have contact mode and non-contact mode, but at present we have some limitation over our instrument. We have only contact mode with us, and we have some limitation over the size of scanning also. Now, as if now we have 5 micrometer scanner is only working, 100 micrometer is not working. And so what all things we will get it from atomic force method. Surface roughness you will get, the trench depth and line width characterization. When you are going to the semiconductor industry, these points are very important. And monitoring the lithography, vapor inspection, cleaning, photomask preparation. In those aspects, atomic force microscopy is very important. These are some images of the atomic force microscopy. So you will get some idea about this. This is an feeling, polymer feeling. You will get the idea about roughness of this one. How you will analyze this? That is very important. You can see the scale and color scale. You can even give different colors. False colors only by using software only we will be giving the false colors. This 20 into 20 sample, 20 micrometer to 20 micrometer area, and we will be getting different colors. Highest area is having 200 nanometer. From here, 3D, you can easily understand the height difference and how hints and values are placed. And from here we will get an idea how much height will be there from the surface, and you will get some values as such as the roughness values, RA values, and all. And different methods are there. By using the same atomic force microscopy, you will get you will get different kind of results. So you can use it as a magnetic force microscopy. So if you want to study the magnetic force on your sample, magnetic properties of your sample, you can use this magnetized tip. We will be changing the tip, and we will be doing the magnetization, magnetic properties analysis. And interesting image, you can see these images. The first one will be the topography of the sample, but when you are going for phase, so you can see an array of, one area is magnetized, other area is not less magnetic property. Like that, you can observe each samples. Here, this is a mix of material, so qualitatively you can identify each one will be how it is placed, each material is placed in this kind of phase image. And this is also very important. Like magnetic force, we want to find out the electrostatic force of your sample. Your sample is having some electrostatic force, electric potential will be there in your sample. You can analyze with EDS microscopy. You will be observing in same way, but with different tip. You will be using a conductive tip, and your sample should be at least somewhat conduction should be there in your sample also. So bottom, as we are doing in SEM, in bottom also we'll be giving some carbon type for conduction. So we'll be applying, we'll be approaching the sample and we'll be analyzing. We'll get some. Hello.
Subash, no problem. No problem.
Okay. So we'll be getting like these images. You can see the interesting aspect of this image. You'll be getting a topographic image as well as you'll get an EFM image. So you see the difference. So we will be selecting at a particular area. We'll be applying a voltage and how the sample is. How sample is behaving, and we'll be selecting another area and we'll be applying different voltage, how sample is behaving. In that way, we can understand what is surface charge of your sample, how it is changing with each voltage. We will be applying some -5, 0, +5 in that range. And next is piece of force microscopy. My thesis was based on this piezoelectric materials. So we'll be doing some piezo force microscopy in this aspect. Piezo force, I think everyone know what is piezoelectric materials are. So when you are applying some pressure, it will give some voltage, in vice versa also. If you are giving some voltage, it will give some pressure in the sense, some bumps and this one. So some local expansion and contraction will be happening. In that principle, we'll be working is we'll be applying some voltage on tip, and sample will be giving some outputs in the sense it will contract, either contract or expand. According. So, and you will be getting the deflections on your position sensitive photodetector, and we will be making it as. And next one is, and so here you can see the potential over your sample. Conductive tip will be using the gold coated tip we will be using for current diaphragm, and this is especially doing for identifying the surface conductivity. And a little bit spectroscopy also you can do. If you want to observe a particular area, how much conductivity is there, you can go for current bias, that is IV graph. This is also possible with diaphragm. So quantitatively you can analyze how much will be there, how much when you are changing the bias, how much current will be formed. And this is very important, this is very interesting. So we'll be observing with IAFM, the electrode, in between electrodes, there is some CNT is there, and we'll be observing the conductance of that CNT by current versus voltage analysis. These things are not done in our facility. These are from some papers. So, but these are the capability of the scanning probe microscopic technique. So these are electrodes, and in between electrode, the CNT is there, and you can observe the conductivity of that particular CNT using IV. And next one is nanolithography. You can pull up pattern some surfaces by using this FM probe, by giving some extra force and blowing the surface with the tip. And next one is oxidizing the tip. Both way you can do the nanolithography. Oh, I hope you know about nanolithography. I'm not going to in details, but different tip will be using here. Diamond-based tip will be using for nanolithography and all. And this is you can write, even you can write Merry Christmas, Happy New Year and all on your tip by lithography. The silicon wafer. This is an oxidation method. The other one is blowing method, and the next one is this one is oxidation method on nanolithography. And next is nano indentation. These the nano indentation will be basically doing for studying the mechanical property in nanotube. So here you will get indent with a Barkowitz tip. I will show you how the tip looks like. This is a Barkowitz tip, and this is also a diamond tip. We will be indenting on your sample, and we can able to understand the hardness of your sample, Young's modulus of your sample, and different mechanical properties of your sample. Loading curve will be, you can see the image, interesting image, you can see that Barkowitz indented area, and you can see the depth, how much it has gone, and by using this loading and unloading curve, you can even understand the Young's modulus of your sample. And force curves also you can plot by indenting. You get some. The first one is far from the surface. The tip and the distance is here. It shows the distance between tip and the surface. First one is far from the surface, and next it will be just approaching the surface, and it will give some pressure over your sample, and it will retract. And again, you can from here you can see the pull-off force and adhesion, how much adhesive your sample is, and pull-off you can do this. and approach, it will jump to contract and it will contract and adhesive force and pull off will be measured. Okay, like this we will get some idea about how much adhesion energy is there in your sample in nano level, some mechanical aspects of your sample. So you can see by observing each graph, you can understand how much large adhesion is there, small adhesion is there. Even if your sample is soft, the graph will be like this, and hard sample will be like this. And this is, I would like to show some images from our own instrument. This is a nanoparticle, how we will measure the nanoparticle. You can measure, you can identify the nanoparticle and you can measure it, how much size will be this below 10 nanometer only. You can measure like this. And this is a fiber kind of polymer material. It is 20 micrometer to 20 micrometer area. Now, as if now it's not possible to do 20 micrometer to 20 micrometer, but we can go up to 5 micrometer to 5 micrometer. This is a polymer nanocomposite sample, helium sample only. So these images are taken by our XC100 microscope only. And this is an interesting aspect of our instrument. So this is from my own work. This is piezoelectric activity. So ferroelectric activity and piezoelectric studies we can study from the AFM image. These are when you are applying, as I already told, when you are applying a different voltage, it will behave differently, and you can understand. You can understand the degree of difference, and you can understand how much it will be varying sample to sample. So I'm not describing more in this aspect, but you can understand, and 5 volt minus 5 volt how your sample is behaving, and 0 volt how your sample is behaving, and plus 5 volt how your sample is behaving. Each one is different samples, and the difference in properties, difference in properties with difference in materials, you can easily study with this study. And this is not from our mission purpose. Dopant profiling you can do by EFM profiling. EFM plus topography imaging dopant. How much dopant will be there in your sample? You can easily for semiconductor EFM you can use, and dopant profiling you can do. And on silicon wafer, if some contamination is there, you can easily understand. Coming from particles on the surface of a wafer, you can understand if you spin coat something, some spin coat a nanoparticle over the silicon wafer, you can easily understand how much size will be there on the silicon wafer and all. But these analysis will be only done with, it's not possible with contact mode. We'll be working with tapping or non-contact mode. It's a irregular surface. Usually, somewhat smooth surface will be going for with contact mode. And titanium nitride gains. And this is depletion transistor. You can see the gate and source like this. You can easily understand by imaging how much accurate your nanofabrication is. How much accurately the source, how much size is there, shape is there, and those kind of things. Even you can see the dopant and all using EFM, because EFM will be measuring the stars. So this is topographical image and this is EFM image. And even you can do by using this auto probe, you can position the tip. You can take one atom and position the tip. I'm not familiar with this technique that much, but still I've seen in one paper, and I put it as a slide. These are the main feasible possibilities of AFM instrument as well as SEM instrument. I think I took more time. Sorry for that, but I think you can able to understand something from my talk. Thank you so much.
Thank you, Subash. As I told in the beginning that Subash has got 9 years of hands-on experience, and it is very clear. It's clearly evident from his presentation. He has given a detailed explanation of the analysis of the SEM, and that is from an SEM image how to read get the more information. Okay, thank you for sharing your valuable experience, and the presentation was also very informative. So we have some questions from the participants.
Okay,
Sir, yeah, I'll read out here in the chat notes. Sir, do our SEM machine has elemental mapping facility?
Okay. Yes, we have elemental mapping facility. I think many of the students are using the facility. But as if now we have some problem with the EDS detector, but our new detector is already arrived, but due to this lockdown and all, it is not installed yet. But now in November 1st or 2nd week, the service engineer is coming and installing, and then onwards it will be working smoothly. We hope it will be working smoothly. EDS, even EDS line analysis, mapping, everything we can do with our unit.
Okay. So next question is, sir, the session was extremely enlightening. I would like to ask that in order to detect cancerous tissues in particular, which form of microscopy is used? And for imaging of biological system, what are the certain measures we need to take? Okay, I too have the same doubt. That is, we have been doing some biological samples, right? What are the challenges in doing the biological samples?
Okay. So in cancer cells and all, as you pointed out, cancer cells and all, I have seen some papers in people are doing AFM imaging with cancer cells, but with our system, it is not possible to do biological samples. But in SEM, as Sajith sir pointed out, we'll be doing biological samples regularly. But the problem is the sample should be completely dried. And another option is environmental SEM. In that, little bit moisture is not an issue. We can do with environmental SEM, and we have equipped with variable pressure mode. We will be giving a aperture in between the vacuum chambers, and we'll be observing in lower vacuum. Okay, so in that level, you can go for biological samples, but still biological samples, we are getting very good images for teeth samples, for some bacterial virus sample, bacterial samples from biotechnology, and a lot of samples are coming from university, from zoology and botany department, but the people are coming with dried samples only. The point is the sample should be dried, then we will get very good images.
We can use a freeze dryer for drying, right?
Yes. Obviously, you can use freeze dryer for drying the leaf or root or some such kind of biological samples. We can go for freeze dryer. We don't have freeze dryer in our facility, but if you come with dried samples, definitely we will be doing. We will gold coat it, and we can easily observe it in our same system.
Okay. Next question is how the latest development are evolving in microscopic field. Will it be possible to view beyond nanoscale in near future?
It's an interesting question. Actually, up to now, it's below 1 nanometer. We can able to go with DEM and itself. And beyond that, I don't know much about that. But in-lens, you recently I have gone through some literature. They are using some in-lens detectors. We are using lenses in our gun area, but in detectors also they are using some lenses and they are capturing minute details of your sample, and we can go up to below 1 nanometer. So in near future, some in-lens FESM is there already. It is there, but they are doing some very good research on that, and I think in near future itself we can go beyond that.
Can we use nano indentation data materials fingerprint?
Materials?
Fingerprint. Can we use nano indentation data materials fingerprint?
Okay. So your nano actually our nano is having a particular shape. So we have some Berkovich indented will be there. As if now we don't have that, but still Berkovich indented is there. We'll be observing that particular area only for the analysis. If your other fingerprints and all are there, we will not seeing that area, but we will be particularly observing that particular area only. Then this way, I think we can able to see the mechanical properties.
Facility here.
Actually, direct PFM facility is not available with our mission. Mission. We have done some in our mission XC100 mission is only equipped with the PFM microscope facility. But for our research, we have alternate arrangements by using some amplifiers and those. We'll be doing some enhanced EFM facilities like EFM as well as DC EFM, that contact EFM. By using this DC EFM, you can easily analyze the what you are getting in EFM in somewhat in that level you can observe in DC EFM. Actually, we are also having that doubt. EFM will be equivalent to DC EFM. I have contacted many of the professors who is working in this field. They are telling it can be equivalent, but it's not equal with PFM. We will get some PFM spectroscopy also. Usually, we will be doing PFM microscopy and PFM spectroscopy. I haven't discussed PFM spectroscopy extensively. DCFM spectroscopy. So by using DCFM spectroscopy, you will get some amplitude voltage graphs. From that, you can identify the clearly identify the piezoelectric ferroelectric nature of your material. You can understand the piezoelectric ferroelectric aspect of your material by using this DCFM. But PFM, if it is not PFM, but you can equivalently available method that is known as DCEF.
And there is one last question. Not EDAX, but elemental mapping is mapping in sample shown in one of the slides. Different elements come in different colors. Is it available? I don't understand the question also actually.
I think he's asking about the colors. Actually, colors we are selecting and we are giving. That's it. It's not an output from a particular sample. We are giving some colors for. We are assigning some colors for each element. If carbon, if we give carbon black color for carbon, it will be the graph will be available like that. And if you are giving red for some other fluorine, so the red dot will be showing fluorine, presence of fluorine in your sample. And even you can do also if you are working with some welded joints. If you want to see the some material, the welded material is gone inside metal. You can draw a line and see the profile of your elements. You already know the elements what you have welded, so you can easily understand the welded joint. Some elements are gone inside to both sides. You can easily understand the profile of your element. You will be giving the different colors. That's it.
I think Anuj,
yes, sir. Dr. Subash, it was nice. Okay, nice presentation. So, actually, I was asking about the elemental mapping. If you have a sample and if you have different elements on the same sample, you can get in the sample itself where these elements are located.
The detector is having some issues, and we replaced the detector with Oxford. And the detector is available for tender, but it is not installed. We are going to install it.
Okay. Thank you very much.
Okay.
Is there any further question from the participant? You can unmute your mic and raise your question. Okay. If there is no further question, so
Hello, sir.
Dr. Subash's lecture was very inspiring, very informative. You have traveled the whole journey from the classical microscope to the present electron microscope. It was indeed very informative. The lecture was wonderful, and thank you for that.
Thank you, sir. Thank you, sir. Thank you very much. We are inspired from you only, sir. Thank you.
Actually, sir, this chemistry department is actually proud of Dr. Subash. He is our own student, and listening a talk from an experienced person in SEM and AFM is very wonderful, actually. So, Subash, I have one query.
Sure, sir. Sure,
It's
sir.
about this AFM.
Okay.
Can this AFM can be used to monitor a living samples? That means a living cell or something.
Sir, biological AFMs are available. In my, I think I don't have any experience in that, but still, we can't able to do it here. But biological AFMs are available. Living samples, I'm not sure, sir. I'm not sure about that. But biological samples, there people are doing with. I have seen some images of cancer cells.
That means biological samples without drying.
Yeah, without dry.
Okay.
In AFM, the advantage is there is no vacuum. There is no need of vacuum. Even in air, in all atmosphere, you can observe in AFM. But in SCM, the problem is with vacuum. Under this vacuum, biological sample as well as the without drying, it is very difficult. That is the issue. Hello, sir.
Yes, I think so, sir.
Is there any further questions from the participants? I think we can wind up, right?
Yeah.
Okay. So as Dr. Sajith told, we are also very much proud of Dr. Subash CK for being with us for last 9 years. Okay. And so thank you, Dr. Subash, for sharing your valuable experience, which can be presented only by a real person with a real experience, real hands-on experience. So now I invite Ms. Vidya, research scholar, to propose the vote of thanks.
Thank you so much, sir. Thank you for the. Thank you. I would like to thank Sujit sir and all faculties in chemistry department for inviting me for this presentation. And I'm highly privileged to be the first person who came out with a postgraduate degree from the same department, can able to give this webinar session of department. I'm highly privileged. Thank you so much.
Ms. Vidya?
Hello. I take this opportunity as a privilege to thank Dr. Subash, our speaker, alumni of our department. Through his lecture, he gave